So you feel like that was a
Very much.
useful outreach?
Yeah, we didn't have that next one.
Yeah, maybe more of that.
I have a question.
Yeah, sure.
Will we be using our slide rules on the test?
No.
Oh, thank
I could do this. I could potentially have a printing of a slide rule, probably maybe, for example, a linear one, not necessarily round, and I could ask you to tell me what calculation it's performing. So I could ask you to like read off what calculation is this slide rule performing in this position.
So we would need to at least know how it operates.
Yeah. You should review the basic, let's say, multiplication and division on the slide rule. You should know how that works. And it's not going to be a major component of the exam, but it might be there in that form. You don't need to bring your slide rule with you. You should bring your yellow calculator or equivalent with you. And the exam will be written format. It will be, it shouldn't be surprising. It'll be questions we've done in our homework for class. It'll be questions you've done in the lab, the drill type questions. Probably, let's say, one question from every category of drilling you've done in the recitation through the weeks. And maybe a couple other things sprinkled in from what we've done on the board. So class notes, recitation problems.
Do you know about how many questions?
That should be it. Depends a little bit on how you group them, let's say. You'll have the full 2 hours to work on it. I don't think you'll be rushed. But it will have to be long enough to basically cover all the things we've done, which at this point it's basically all of the elementary functions up to this point. Our trig functions, our powers, our exponentials, our logs. Okay, let's continue a little bit with our circular motion and discussion of radians. Was everything from the circular motion, and we didn't do circular motion really, but was everything from the radians discussion clear to people last time? Okay. So let's review real briefly, and then we'll extend a little bit these ideas to a few application problems. So the basic notion, once again, is that if we had a string, the length of the radius, and we stretched it around the circumference, we could measure radius lengths around the circumference. And each of those points would correspond, obviously, to a certain opening angle. And that's how we define the angle in units of radius lengths. So as we say, the angle in radians is its arc length in multiples of the radius. I don't mean anything there about capitals versus lowercase. So the angle is the arc length in units of the radius. If that's the radius, this would be 1 radian. That's in the ballpark of half a radian. So 1 radian, 2 radians, 3 radians, pi radians, 4, 5, 6, 2 pi. Good. And we can convert back and forth by similar proportions. The angle in degrees is to 360 degrees, as the angle in radians is to 2 pi radians. Let me say that one more time. When you write down this equation, I don't want it to be something memorized, but something you understand and almost read like a sentence. The angle in degrees is some portion of the full circle in degrees. The same portion as the angle in radians is a full circle in radians. So So all the way around is 2 pi radius lengths, 2 pi. Okay, so as we were suggesting last time, this is not just another way of doing angles. It is in some sense the natural way of doing angles. Especially as we start to work our way towards calculus, especially as we, before that, work our way towards discussion of circular motion. This is absolutely and unequivocally the natural way to describe angles. Now, having said that, it is a little less conversant, at least for people who grew up used to degrees. The nice thing about degrees, again, is that it's so evenly divisible by all of these numbers. Everyone knows exactly what you mean by 45 degrees. To convert 45 degrees to radians, it's going to be some crazy decimal, and there's not one that I quite have in. If that's pi, this is pi over 2. So 45 is pi over 4, 3.14 over 4. You have to think about it a little bit. It's a little more than 3/4. But you have to think about it. I don't immediately know what that means. So degrees are great for conversation. We'll do plenty of problems still in degrees. But for certain applications, we definitely want to be in radians. Now, when does it make a difference? In some sense, when do we normally encounter angles? More often than not, we encounter them inside of trig functions, right? If I write something like sine theta or cosine theta, it doesn't matter what I consider theta to be. You know, in my mind, I may imagine that it's in degrees or radians, but whatever it is, I imagine that the sine and cosine is being evaluated, obviously in the context that's appropriate to my view of the angle. It doesn't matter. The sine of the angle has some physical reality to it, and the sine of that angle is a number, regardless of whether I consider in my mind that physical angle to be in degrees or radians. Right? So in some sense, whenever that angle is wrapped up inside a trig function, it doesn't really matter what I imagine it to be. But whenever the angle is running around 3, it matters very much whether I consider it to be in degrees or radians, because I'm discussing the size of the angle itself, and the unit system that I impose on it in that case is very, very relevant. When does it matter for your calculator? Well, if you're going to take an angle and plug it into a trig function, and you already have in your mind what unit system that angle is, you better make sure that your calculator has the same sense of what unit system you're using. And then conversely, if you have the value of a sine or a cosine or a tangent, and you want to read into the other column, in other words, use the inverse function, then you need to tell your calculator what type of answer you would like back so that you can interpret it correctly. Other than those cases, it doesn't matter what mode your calculator's in. For example, we're going to be doing some circular motion coming up here pretty immediately. And the discussion for the context for circular motion is absolutely going to be radians. It's just absolutely going to be radians for reasons that will be 100% clear in just a second. Not clear right now. But that doesn't mean as we're adding and multiplying and dividing these things that your calculator needs to be in radians. These are just numbers that we're adding and multiplying and dividing, and your calculator doesn't care. When does your calculator care? Basically speaking, only if you're taking a degree, taking a trig function of a degree, or taking an inverse trig function to give you back a degree. In those cases, you and your calculator need to be clear on the unit that you're feeding in, or for the inverse trig functions, the unit which you are expecting to receive. Makes sense? So we're going to start to talk about circular motion here. And we're going to start off with our just defining relationship for the radian measure. The arc length S is some number of radius lengths. That's the way to read that equation. The arc length S is some number of radius lengths. some number of radians. So what we're going to imagine is a scenario, let's say, where we have an object as time passes, which is moving around in a circle. This could be a car driving on a track. It could be, let's say, a pottery wheel which is spinning, and maybe there was just a spot of clay at the edge of the wheel that we're keeping track of as it goes around and around and around. Anything like that. It could be a figure skater who is spinning around on the ice. Any sort of rotating system. Now what we're going to do is follow this ladder down a couple of rungs, almost exactly like we did for linear motion. What we're going to do as we follow that ladder down is look for the change relative to a change in time. So we're going to write this as change in S divided by change in time. Now, if we do that to one side of the equation, obviously we'd better also do it to the other side of the equation. So R delta theta over delta t. Now, I've made an important assumption when I perform that operation. I've implicitly assumed that something is true. Does anybody notice what I assumed? That's exactly right. I'm assuming that the radius itself is not changing. So in other words, what I did is I moved the changing sign, which in some sense, if I'm applying it to this, is applied to all of that, right? But I moved the changing sign right through the R, and the R is a constant. Now, as we get a little farther along in the semester, this idea of taking ratios of changes, if we had a graph, it would be like a slope, right? If S was our vertical and theta was our horizontal variable, this would be like a slope, right? This process of taking relative changes, let me just warm you up a little bit. That action of taking relative changes is what we're going to call a derivative a little bit further along in the semester. It means taking the slope of something, it means taking the rate of change of something. Specifically, when we talk about a derivative, we're going to mean a ratio of small changes. And to indicate that we mean small changes, rather than using the symbol delta for change, you know what symbol we can use? So delta is like a Greek D. So delta, you've kind of gotten used to. Delta means the change in, or sometimes it means a little piece of. Yeah. If that change in or that little piece of is finite in extent, we'll write it as a delta. But if we take it in some sense as small as possible, only small changes, yeah, infinitesimal, we'll write a D instead of a delta. It's just to prep you a little bit for what's coming. So don't get scared when you see that D. What it means is we're just taking small changes. So for example, when would that be relevant? When is there a difference? You imagine you had some graph that looked like this, y and x, right? So I would say, well, what's the slope of that? What's the slope of that line? And you might say to me, well, at what point? Because there is no single slope, right? This is a line whose slope is continuously changing. Now, if you did something like this, delta y, delta x, right? Then you would get a slope like that. But does that really characterize the line? No. Right? What you've actually got here is an average slope over that interval, right? For an average, you've got the total y change and the total x change. On the other hand, you could imagine, ever see that? You could imagine that slope following the curve and existing at any given point, right? So these steps are too big to really characterize everything that's happening along that line. But you could imagine couldn't you cutting it into lots of smaller steps?
Essentially like a definition of calculus.
That's what we're warming up to. We got it. And you know, even this, you say, oh, that's too big. Well, I could imagine cutting that into little smaller pieces, right? And those are little changes in Y versus little changes in X. And as long as those things get sufficiently small so that there's not large changes happening along the difference. Being a little fuzzy about some of those words, but I think they're reasonably intuitive. Then we'll have something which is an instantaneous slope rather than like an average slope over a longer. Everybody buy that? So that's the difference between the delta and the D. Intuitively, they both mean either change in or piece of. And depending on the context, it'll be one of those things or the other. And if it's a finite piece or a finite change, delta. But if we're making the steps really, really small, kind of as small as can be, as infinitesimal as the lingo, then we'll write it as a D to keep that separate from the delta. Now that you're all comfortable with D's, let me just go ahead and write it. Now this thing, the ratio of distance to time, what's that?
Feet?
Yeah. Yeah, both right. It's a V. It's what we might call, we're going to be a little bit more specific, the tangential velocity, the velocity along the curve perpendicular to the radius. This thing is an angle per time, right? It's an angle per time. We're just going to introduce a name for that. We're going to introduce a symbol for it. It's what we're going to call the angular velocity. That's what we're going to call the angular velocity. And we're going to introduce a symbol for it. That's the Greek letter, and we know what that Greek letter is? Woo.
The W,
That's omega?
That's omega.
That's
That-
a lowercase omega?
That's lowercase omega.
Okay.
Capital omega, which you've seen, looks like that. And that symbol gets used for ohms, which is a measure for resistance.
and notation.
Yeah. That's capital omega. This is lowercase omega. It's not a W. It's a little curly, kind of scripty W. If you read it, you should read it as omega, if you're pronouncing it in English. Or, if you want to refer to it as what it is, you can call it the angular velocity or the angular speed. In certain contexts, you'll also see the phrase angular frequency. So angular frequency is also a pseudonym. It's also called W. It plays basically the same role. It's just a slightly different context interpretation. So angular frequency, angular speed, angular velocity. See those things. So, by following our ladder down one step, we've got a new equation. V is R omega. Now, this is a very important equation. Probably deserves to be in your memory banks.
Is that VT?
Yeah, it is, although we usually leave that off. But the tangential velocity is a better descriptor for it. So V is R omega. You should understand about that equation, though, that it's nothing other than our definition of radians. This is where we started from. We're taking our definition of radians, we're just writing the ladder down on top. The reason that this is so useful, let me show you here. The reason that this is so useful for describing spinning objects is as follows. Imagine that you were out at the racetrack. And imagine that there was, sort of a crazy race going on this day out of the racetrack. Imagine that there was a horse. Person. Sports car. Is it a fair race?
The way that it's set up, maybe.
Maybe. How could? What do you mean by that?
Well, as long as you're talking about like, I guess in radians, like, then the distances would be much shorter for the man going slower, more for the horse going faster, and even more for the car also going faster.
Yeah. In principle, I could set up this track that it's just that it might be a very interesting race. You see what I mean? If I compensate for the fact that the person doesn't have to run as far because they're at a smaller radius. So imagine as they go around the track that they're all keeping in sync with each other. They're all keeping in sync with each other. Now, you may say to yourself, well, that's not a very realistic situation. Okay, let me give you a situation that is realistic. A pottery wheel spinning. The stuff that's out at the edge of the pottery wheel is moving faster. The stuff that's in the middle of the pottery wheel is moving slower. And we turn out to be interested all the time in things that are rotating, and the things that are farther out at the edges are moving faster, and